And what this will do, did it not work? There we go. So it'll select all those faces on the patch here. And then we can refresh this, and go back, and it'll add that additional refinement. So this is good if you just want to refine the faces. You can do this in Snappy as well. It's just as easy. Or we can do it another way. Okay, so we have our initial conditions set, and I'm actually gonna do this in parallel because it's quite a bit faster. Okay, so we're gonna run this. Okay, so it's running. Okay, so, and actually while we're doing this, we can look at some of the other files specific, or like the dynamic mesh dict, which is going to be, there we go. So if you want to use AMR, by default, you don't have to have this dynamic mesh dict. It'll automatically do a static mesh. However, if you want to use some adaptive mesh refinement or a moving mesh or anything like that, you have to add this optional dynamic mesh dict to the constant folder. And then we need to specify the dynamic mesh type. So we're going to be using the adaptive FE mesh. What this is this is the blast foam specific mesh type. So it uses things from the reference that Peter had mentioned earlier that has that adaptive mesh library. However, it's kind of been expanded and tweaked a little bit, really, for blast and compressible specific things. So here we use error estimators to estimate where we need to refine. So we're going to be looking at the density gradient. Basically, wherever you have strong gradients, you want to refine that area. We also have this option to protect patches. So what this means is don't unrefine or refine the patches after they've been set in the initial conditions. So this means that any cell along that patch, don't touch it, basically. Okay, next we have this refine interval, which we have set to 2. This basically means every 2 time steps, check refinement and refine as needed, refine and unrefine as needed. Then we have this load balance section, which basically tells us how we want to balance the mesh during runtime. I think these are all the default properties. The method is defined by whatever you have in your decomposed project. So if you have something like a simple method, which is a static, essentially, it'll do a terrible job always. So you want to do something like Scotch or PT Scotch or Metis or something like that. They're just different methods to actually balance the mesh. Next, we have this lower refine level, which basically says, okay, so what error do I want to stop refining or start refining at? So if the error is greater than 0.1, I'm going to refine. If it's less than that, I'm not. We have this unrefined level, which says, okay, if my error is less than 0.05, I want to unrefine it. So in between 0.05 and 0.1, it will do nothing, but on either side, I'll either unrefine or refine. Again, we have this number of buffer layers here, which is how many cells between each level. And then we have the max refinement, which says, how many times am I going to refine the mesh before I stop? So we're only using 2 here. This gets much more expensive as you do it during runtime. So for every additional level that you have in 3D, it's 8 times as many cells. 2D, it's 4. So it adds up very quickly, especially in 3D. And then this last option here, dump level. Do you want to write the cell level? Okay, so it's just kind of a quick overview of that. And then we will look at our case now. So we're just going to look at the internals. Actually, no, I will also add a contour. I'm actually going to change this contour. So instead of using volume fraction, we're going to use, we're going to use the pressure or overpressure. So we will specify the overpressure to 0. So basically wherever we have 0 overpressure is going to be where we want to contour. Let's go 1. Yep, there we go. Okay, so some other things you can do with these contours, say you kind of want to see through it. You can specify the opacity to some lower level, and that way you can see through. So here we're gonna look at our overpressure. Okay, so I'm gonna turn off the edges. Okay, so here we're just gonna play it as it goes. So you can see the contour expanding. So this is 1 Pascal of overpressure. It's going to interact with the wall, kind of curve around it. Okay, so this is roughly what it looks like. All right, so just some other quick things to mention. So in this case, share the phase properties real quick. Some other things that were added very recently. So when specifying the activation points, so where you want your detonation to begin, we also have this new use COM, which is basically use the center of mass. So rather than specifying a point, which we did, so if you move your charge, you have to move the point here, otherwise it'll get messed up. You can just use the center of mass and it'll detonate from the center of the volume fraction, basically. And you can also use these points and use center of mass with the pressure base and Arrhenius right now. So it makes those a little bit easier to use. All right, so lastly with this case, just touch on the control dictionary as well as some probes and other post-processing utilities. Okay, so here in the control dictionary, which we haven't really talked about yet, so we specify this application. This application is really only important if you're going to be using the get application. Right. Yeah, get application call or command line program, I guess you can call it, or executable here. So it'll basically read the control dictionary and find out what application says. Then we have the start from. So we want to start from the start time. You can also start from latest time, which will look for the last time you have, and we'll start from there. Start time is 0, stop at the end time. We have an initial delta T, write control, write interval, so how often do you want to write? Yeah, some other stuff. It's all fairly explanatory. Write cycle, I'm actually not sure on. Write precision, you know, how many decimals do you, what precision do you want? Do you want to compress it? Yeah. So the important part that I would like to talk about here is going to be this function section. So in here, you can add some additional things that will basically allow you to output additional information. So by default, you just have the output of, you know, mass, momentum, energy, temperature, things like that. But if, you know, say you want to calculate the impulse, we have a utility to do that. So you add this section here. So this name here is basically just the name that it'll use to denote this object. The type here is what you actually want. So this is of type impulse. You could call this whatever you want. So here we'll calculate the impulse using a reference pressure of 1 atmosphere. And we're going to be writing it every write time. So what this will do is it'll output the impulse field. So we can look at that real quick. So this is going to be the impulse seen. So this is the overpressure integrated over time. So in addition to that, we also have the actual overpressure function, which again basically just subtracts whatever the reference pressure is from the actual pressure. So you can do this in ParaView. However, this is just something to make it simpler so you don't have to. And again, this is going to be using the reference pressure of 1 atmosphere. And then we also have this option to store it. So basically this means, do you want to use it any other time besides to write? If this is no, basically what it'll do is it'll create it, calculate it, write it, and then it'll be gone. So we would like to use it to calculate the maximum pressure and impulse seen at all time. So this is going to be a field max function is what it's called. And it's going to write it every write time. However, it'll store it for everything else. But we want to look at the overpressure and the impulse. So what that means is, so we can look at the maximum overpressure. Look at this in log. And it'll look kind of weird just because of the way the AMR works. However, you can see that as it expands, this will just track that maximum value of overpressure seen at every cell ever. So this checks at every time step. And it'll do the same thing for the impulse or whatever field you want. All right. Next, so sometimes, a lot of times, the volumetric data can be very expensive to process. So we have some options to sample surfaces. So here we're just going to be calling it surfaces. You can denote, or you can create multiple ones of these if you want different write intervals or anything like that. We're going to be outputting this to VTK. So this will create VTK surfaces of just the pressure field. We're just looking at the pressure. So we want to output the ground patch. We want to output pressure contours. You can do any contours you want though. And then we're going to be looking at some planes. So just the Z normal plane, Y normal, and X normal. And basically what these will do is it'll create surfaces within the post-processing directory of all of these files. So okay. So here, if we look at the post-processing, we can see, so these are all of the functions that we're going to be using that are written. But we're going to be specifically looking at the surfaces. And we're just going to look at one of these. And then, so what it'll do is it'll write all of these files to whatever the field name is underscore whatever field you're looking at. So ground, P contours, X normal, Y normal, Z normal. So unfortunately, by default, OpenFOAM is very annoying with how they do this. You can't actually view these in any sort of good way within ParaView. However, so I'll show you what it looks like briefly. So you get all these folders and you can view it like this, but that's it. If you want to view the time series, you really can't. So there's two ways around this. You can either use the blast to VTK, which what it'll do is it'll create symbolic copies within this VTK file. And it will, that way you can look at the group of them. So here we have the grounds, and it'll open all of them up. And you can watch as they continue. So if you don't need time or anything like that, this is good. However, if you are interested in viewing the time, which it's a lot of times just easier to look at, you can use the create VTK time series. And what that'll do is it'll create a single file that you can open up that provides links to everything you need. Then it'll allow you to look at the times. So this is generally a better way to do it. Basically just, it writes everything, or it gives you all the locations so you can look at the time as well. So these are pretty useful if you just want, have really big cases, volumetric data is really expensive to look at. This is an easy way to do that. Okay, last section will be on the probes. So these probes, these are points in which you get time series data from. So we have had some added some additional features to the standard OpenFOAM probes utility. So we want to use a probes. We want to sample this at every time step. And the things we've added specifically are the ability to adjust locations. So what this will do is if it's outside of the mesh, it'll basically move it to the closest face, and then just use that. And you also have the option to append to existing files. So this means that if you restart from a later time, it'll look up whatever you were using before, whatever probe file, and append to that. So this is super useful if you don't want to have to merge all these probe files. So here you specify the probes, the probe locations you want to use, and then the fields you want to probe. And then within the post-processing, and then we called it p-probes, you will have the time at which it starts, and then within that folder you will have the files. So we'll change directory here. So we'll use GNUplot, and we'll just plot the pressure. So this is a good way to just see some data. So here we have our pressure. Not exactly sure what's going on here. So yeah, this is basically how you would do it for everything. You can include as many probe locations as you want. Yeah, it's really good to look at time series history. All right. So that is it for the building 3D. And then very quickly, we will also go through the Kingery-Bolnisch case. So this is a validation case within the standard code. So this has already been run. It takes a little bit of time. Okay, so here we start. This is a spherical charge that's detonated on the ground. And basically it's allowed to detonate. And then we watch as the pressure wave expands. And then what we're going to be looking at is we're going to be looking at the maximum impulse, maximum overpressure, and then the time of arrival in comparison with the standard equations. So there really isn't anything different about this case. We're going to be using a wedge. So here we have the wedge. We are going to be using a C4. Going to be using TNT. And then we're going to be using the linear detonation velocity detonated from the origin. And then, yeah, it's expanding into air.